Hi everybody, Dennis Graver here to talk about our hands. Actually, no, we're going to talk about molecules that are chiral. Chiral comes from the Greek word referring to our hands. So it turns out molecules have something similar to our hands. Talk about that right now. Okay, so this is a real subtle topic. Not black and white. It's a little difficult to understand. So be a little patient with it. Come back and replay certain parts of this video if you don't get it the first time through. Okay, let's give it a go. Chiral molecules. They are a different type of isomer. Another type of isomer. So remember, isomers are different molecules, but they have the same chemical formula. And then here are two chiral molecules. And you look at these and say, wow, they are incredibly the same. Aren't they the same? 4 carbons in a row, 4 carbons in a row. An alcohol group off of carbon number 2. So they actually have the same IUPAC name, do they? And then the only difference is the alcohol group is on a bond that's fading into the distance, the wedge, that's a dash, the dash bond. Whereas the other molecule has the alcohol group coming towards us on a wedge. And it turns out this one name is trying to describe 2 different molecules. So actually, this is an incomplete name. In our next video, we'll fix that. Today, we're just introducing the idea that molecules can be incredibly alike, this molecule versus this one, but they're subtly different. And here the difference is the alcohol group away or towards, and the corresponding hydrogen could be away or towards. And as people start looking at these types of isomers, they realize they have a lot of similarity to our hands. And so they got in the habit of calling one of these molecules the left-hand form and the other molecule the right-hand form. More on that in a second. Right now, just wanted to give you some other terms, right? Because scientists love putting new names, new labels on every new idea. So now molecules have handedness. Ooh. So when you have a pair of these molecules, how can you use what kind of words can you use to describe them? Well, you can say they're a pair of chiral molecules. They're a pair of stereoisomers. That's an interesting word, huh? We know what isomers means. 2 different molecules, same chemical formula. The stereo, that reminds me of surround sound, 3-dimensional sound. And that's the reference here. We're talking about 2 isomers, different molecules, same chemical formula, but they're so incredibly alike. The only difference is a 3-dimensional difference, alcohol towards us or alcohol away. So that's a decent name. That's quite descriptive. This one's not. A pair of enantiomers. I should go and look up and see how that word was derived. I just remember, if you hear enantiomers, we're talking about chiral molecules, and we have a pair, right? A pair of enantiomers, a left-hand and a right-hand form. One way to test in the laboratory whether or not you have a molecule that possesses handedness, whether or not a molecule is chiral, is to see if it can interact with light. And if it does, we can label it a pair of optical isomers. Yeah, more on that in a few minutes. This is another way. This one's also very descriptive. A pair of non-superimposable mirror images. All right, let's explore that last one a little bit more. But before I move on, I need you to be familiar with all 5 of these terms because they're used interchangeably. And it's not just for Unit 1, and we're going to see it throughout organic chemistry. And you will continue to see this in biology and biochemistry. Okay, so we got this idea, a pair of enantiomers and non-superimposable mirror images. What are we talking about? Okay, well, I found this and stole it off the internet, and I thought this is a good biological example. You may have heard of lactic acid. It happens when you're you're doing a lot of exercise, a lot of activity, physical activity, and your muscles start to burn, right? You're in the gym and exercising, and what is that burning sensation? You're overusing your muscles. Well, your muscles are not getting enough oxygen, They still need energy, so they're breaking down blood sugar, glucose, but without the oxygen, they can't convert glucose all the way to carbon dioxide and water. So it stops, the breakdown of glucose stops at this molecule called lactic acid. But why does it burn? Because acids kind of sting. And where's the acid part here? Right here. You need to know your functional groups. This HO2C is the condensed formula for this group, which you can recognize as a carboxylic acid functional group. Sure, lactic acid's an acid, it's gonna burn. It's like, you know, it's acidic. Okay, turns out our bodies only make, let's call it the left-hand form. What are we talking about? We're saying that same idea over here, you have two forms of this alcohol. Sometimes the OH group's away and sometimes it's towards us. Well, the same characteristics here too. So we got the natural form that we find in our muscles after heavy exertion, lactic acid, the left-hand form, maybe the negative sign. I'll talk more about that negative sign in a minute. But if you make the rear, you know, if you, how do we start? Take the other isomer, the other enantiomer, the other stereoisomer, it would look like this. So now how are these different? Well, both hydrogens are up and both methyls are towards us. So maybe we'll start there. The HC methyl group. HC methyl group. They're oriented the same way, up and down. But in this form of lactic acid on the left, you got the carboxylic acid on its right. Go over here, and you have H up, C here, methyl down here. Now the carboxylic acid's on the left side. And that's the only difference. And in a minute, let's see if we can convince ourselves that these two are in fact different molecules. But here's something else to consider. If we take this first molecule and bring a mirror nearby, that's what this is supposed to represent, a mirror. And look at the reflection. So this molecule casts a reflection on the mirror. We'll take a look at this reflection and compare it to the other molecule. They're identical. So the mirror image of this form is the other enantiomer. Okay, so now we're breaking down this other way to define chiral molecules. We can say that they're mirror images of each other, but they also must be non-superimposable. Okay, so what do we mean by that? Well, grab this molecule and put it here. It's kind of in the back. And then grab this molecule here, and you need to spin it. Sorry, so take this molecule, put it in the front, we spin it. What we're trying to do is line things up. So we can line up the C and the H, line up the C and the H. We can line up the OH, line up the OH. Good, everything is superimposing if we try and push this molecule on top of this molecule. But it doesn't work because the carboxylic acid doesn't line up with the methyl group. It's a mismatch. And then here, the methyl and the carboxylic acid don't match. So then what was done, let's see what they do. They kept the back molecule the same, going over here. The lactic acid is still the same orientation in the back, but they took the forward molecule and they spun it yet again. So they moved it, rotated it, so the alcohol group was pointing up. Alcohol group's pointing up. And they did that to try and make the carboxylic acids line up. Now they line up here. The methyl groups are lining up here. But now we have a mismatch between the H and the OH, the alcohol and the H are mismatched. And that's one way to convince yourself that these two molecules are different. Look incredibly alike, but they're different. All right, so it's very much similar to our hands. So these two hands, hold up your own hands and you'll convince yourself they look incredibly alike. And my hand's different from your hand. Especially if you go this side, you can't really see it in this video. This side's pretty hairy. There's a no hair side and a hairy side. There's a ring here that's breaking the symmetry, so ignore the wedding band. But if you line things up, superimpose things this way, hey, everything lines up. Aren't these the same? And the answer is no. One side has hairy side up, palm down. The other one's palm up. So you to properly line things up, you need to put both objects, if you're testing for chirality, in the same orientation, palm down here, and then see if they line up. And no, there's a thumb on one side and a thumb on the other. Only if I do it this way. Got a mirror behind me, kind of see it. But if you look, it's not going to work, it's too far away. But if you take that image right there, and look at this hand with the ring, they are in fact the same. The mirror image right there is the same as this. Okay, they're mirror images. My left hand and right hand are mirror images of each other, but I cannot superimpose them. My hands are chiral. Oh wait, the Greek word for hand is chiral. So my hands are hands. That's what I'm saying. Okay, but let's talk about molecules because they possess the same property. Mirror images of each other, but you can't superimpose them. So, got my model kit out. Let's see if we can hold it up so you guys can see it. I got a green, a yellow, and a red with a white. You can choose whatever elements you want. Sulfur, chlorine, oxygen. Well, not oxygen because it bonds. I got these bonding one time. So maybe these are the halides. Fluorine, chlorine, and bromine. Who knows? I built another molecule with the same atoms. So I'm going to grab the hydrogens. Hydrogens I'm holding on to. And I got the yellow over here. I want to see if I made the same molecule twice, or do I have different molecules? So what you can do is see if you can superimpose them. So I'm going to try and get the yellow and the white to overlap. Ooh, they do. Oh, and look, the red are overlapping. And so are the green. Everybody's overlapping. Everybody's superimposing. I made the same molecule twice. Okay. So that's kind of boring. So I'm going to take this molecule and I'm going to pick any two, break bonds. Ooh, you're breaking bonds? You have a chance to make a different molecule. No guarantee you will. I spilled over my coffee. Let's see, and I wasn't paying attention because I knocked over that. Let's see if I actually made a different molecule. So let's grab the hydrogen. Got the hydrogen, line up the yellow ones, and yeah, I wasn't paying attention. Try again. That was actually the same thing twice. There we go. Try that. I think I swapped them this time. Line up the yellow with the white. Ooh, the green and the red are not lining up. Okay, we'll make them line up. There we go. Now the green and the red are superimposed, but not the white and the yellow. Okay, well, superimpose the white and the yellow. Okay, they're lining up. Well, that messed up the green and the red. Okay, there's no way to spin, twist, rotate this to get it so everybody lines up again. They're different. One's a left-hand form, the other's a right-hand form. So if you don't have model kits, that's okay. They're kind of expensive. Go get some toothpicks and marshmallows or gumdrops. Make your own model kit. They're with your own hands. Okay. So molecules possess handedness. Not all of them, but some of them. Okay. We did the overlapping test. Now on an exam, you're not going to get a model kit. So we're going to need some other tests to see if molecules possess handedness. And we're going to get to that shortly. Okay, what's our next type? Oh, quick review now. So far we've seen a lot of different types of isomers. So isomers are different molecules, but they have the same chemical formula. And one category might be structural isomerism. Isomerism, weird word. These two molecules have the same formula, but one's straight chain, one's branched. That's one way to make isomers. Second way is, hey, three in a row, chain's not branched, but the halide, the halide could be in the middle or it could be at the end. These are now different molecules with the same chemical formula. You could like scramble up the groups. So we have an alcohol group here, and now we have an ether group. But if you check the chemical formulas, they're the same. But these are clearly different molecules. One's alcohol, one's an ether. Okay, another way to make isomers is a three-dimensional variation. So we saw cis and trans. We previewed the double bond group. So if you, the alkene group, if we consider a line going through the double bond, here the two identical groups, our bromine, are on the same side. And here those two identical groups, bromine, are on opposite sides. And because the double bond can't rotate, there's no way this molecule can change into this one. They are different molecules. We also saw this fact in rings, right? So if we have a ring, cyclopropane, and we attach two bromines on adjacent carbons and put them on wedge bonds so they come out towards us, both these bromines are on the same side of the ring. But that's different from when one bromine's below the ring and the other bromine's above. This is the trans isomer, and it's different from the cis isomer. And because of the ring, you can't rotate these single bonds to make this bromine go in the back and keep this one in the front. They're different molecules. And today we're seeing our third type. One way to describe this, this additional type, one way to describe them is say that they're optical isomers. And so over here, there's another term, enantiomers, where now we have mirror images of each other. You can have other types of mirror image properties we'll see again near the end of this video. And there'll be another word, diastereomers. Yeah, I'm gonna save that for another video. But this is a nice graphic, nice slide. Rewind it a little bit, take a screenshot before I marked it all up. Or sorry, go to the Canvas and download the key concepts, part 6. And then you can mark it up however you like. Okay. Ooh, we also talked about Newman projections and chair flips. Are these two isomers? No. Remember, isomers are first different molecules, same chemical formula. But when you do a chair flip or you do a Newman projection and you twist the molecule into a new shape, you're dealing with the exact same molecule. It's still, right? This is still 1-methyl cyclohexane. And now this molecule looks different than the first one. It's still 1-methyl cyclohexane. It's the exact same molecule, same chemical properties. It's just wiggled itself into a new shape. These are not isomers. Oh, and I might as well complete this whole analogy or this whole description here. None of these are resonance structures. Resonance structures are for a single molecule. So if you draw one resonance structure, then another, they're all the same molecule. The key thing is you cannot move an atom from one resonance structure to the other. You can only move electrons. And so these are not resonance structures because we did move atoms. Right? The methyl group is axial, and now the methyl group's equatorial and moved. These are not resonance structures. Conformational changes are just changes in the same molecule, so these are also not isomers. They're different shapes, different conformations. I know, lots of things to know in organic chemistry. So give yourself some time, make lists. That helped me when I was taking this class. Make lists and write things down and go back and review that. Moving on, what do we need to know about enantiomers, optical isomers, stereoisomers, chiral pairs of molecules? First of all, they're amazingly similar, right? So if we go back to the first pair of enantiomers, these two alcohols, oh my gosh, the OH group can hydrogen bond. So both molecules are very soluble, well, not very, but they're both soluble in water. There's 4 carbons, there's 4 carbons here. They can get into the same, if you draw Newman projections, they're going to have the same energy minimums, gauche and eclipse, and well, that's an energy maximum. And what's the other one? Anti-conformations. You measure the boiling points, the melting points. Look at the color of the molecule. Measure the density. They are the same. So enantiomers are incredibly alike. They're very difficult to tell the difference in the lab. And if you have a mixture, it's very difficult to find out that you have a mixture of enantiomers. And even more difficult to get one enantiomer away from the other. You can throw in an acid, an oxidizing agent, a reducing agent, do some funky chemistry on it. They react at the same rates. They give you the same types of products, incredibly similar. The only differences are that chiral molecules, like our left and right hand, can interact with other chiral molecules or chiral light. I make the analogy in the classroom that, you know, if you stick out your right hand and shake my hand, that's the proper way to shake hands, right hand to right hand. I don't know proper, but it makes a good fit. But if you keep your right hand out, but I bring in my left, that's just awkward. You clearly can tell, hey, you're using the wrong hand. I can tell. Give me the other enantiomer. You know, give me the proper hand. Molecules react the same way. As long as both molecules, both objects, I guess I should say, are chiral. So in the lab, there's two ways. Light can be chiral. We call it plane polarized light. And this brings us to the other term for enantiomers, optical isomers, because one enantiomer will interact with light differently from the other enantiomer. The other way is how they interact with other chiral molecules. So if you have one reagent that's chiral and you have a pair of enantiomers, each enantiomer reacts with that chiral reagent differently. Cool. All right, let's talk about optical activity and a cool little device called a polarimeter. Can I get this on the page? Almost. Okay, you can skim through this paragraph, but I'll go over in a second. Here's the device in the laboratory called a polarimeter. We just have a light bulb, light source. And what is light? If you haven't had any physics yet, think of light as a wave. So an oscillate this way, a light wave. I drew the oscillation up and down, but I could have drawn it this way, the light wave going down. And now I go swing to the left and swing to the right, swing to the left, swing to the light. The light ray is oscillating left and right. And that's what's happening here. As light comes out of the light bulb, it can oscillate up, down, left, right, and all angles in between. It's unpolarized. We have light rays coming out of the light bulb in all different orientation. There's a cool device called a polarizing lens that'll block out all the light except for light that's vibrating in the same plane as the polarimeter. Now, if you have a polarizing lens, you can't see these lines, but it's helpful to draw them in so you can understand what's happening. If the light comes in vibrating left to right, it gets absorbed or blocked by this lens. But if the light is vibrating up down, in line with these little slits, if you will, that's not actually how it works, but think of it as little openings. It can just vibrate right on through. The wave can bounce up and down, oscillate up and down, and make its way through, going up and down. That's what this line is right here. That's representing light making its way through the polarimeter, sorry, polarizing lens. It only goes up and down. And then right here in our polarimeter, we have this chamber, glass chamber, and we fill it either with a pure molecule that is chiral, or we dissolve it in a solvent. And depending on how many molecules are in here, turns out as the light goes through here, something cool happens. The plane of oscillation will rotate. So weird. I don't quite understand what's going on here, but if you put a chiral molecule in here, the light used to be bouncing up, down. As it goes through the solution or the pure compound, the light will actually rotate its plane of oscillation. So maybe now it started up, down, it comes out left, right. And if you have a polar lens still oriented up and down here, all the light will be blocked. Instead, you have to rotate this second lens so you're lined up with the oscillation. And the amount of rotation it takes so you can see the light come out is called the angle of rotation. And that's how you detect that, hey, this molecule just twisted the plane polarized light. And you can measure how much it was rotated by. And now you have a test in the laboratory that, hey, this molecule must be chiral. Because if you put molecules that are not chiral, don't possess handedness, the light goes through unchanged. It enters going up, down, and comes out still up, down. Cool. So that's the quick little breakdown of how a polarimeter works. And the main ideas are, one, you got plane polarized light. I like to think of it as chiral light. Again, a little physics. When I draw a light wave doing this, we're talking about the electric field of light, the E field. So, kind of weird. But here, light actually is involved. It's similar to electricity. It's called electromagnetic radiation. So with light, there is electric field associated with it. And as it vibrates, sometimes electric field points up and sometimes it points down. And then it points up and points down. So it oscillates back and forth. And here I'm showing it up, down. But light also has magnetism associated with it. And it turns out the magnetic field is coming away at a 90-degree angle. This is coming out towards you. And then as the wave oscillates down here, it actually, the magnetic field, they label it as a B field in physics. The B field will actually be away from us. And if you look at the combination of that, or just look at, maybe the combination of the E and the B field, the average would be here, and now it's down. So if I average it together, this might be the sum of the two vectors. I don't want to get too deep into the physics, but that's what's happening here. And then you look at the sum of these two vectors, and as you watch this sum of vectors go through this oscillation, it's going to rotate. And depending on how you look at the light ray, that rotation either goes left-handed, like clockwise. They just said it. It either rotates clockwise or counterclockwise. One or the other, not both. And that's how I think of light as being chiral. It's either a left-hand spinning light ray or it might be a right-hand spinning light ray. Weird. That was too much detail. Plane polarized light, that's all you need to know. Oscillating up and down, put in a chiral molecule. If that light ray rotates its plane of polarization, it's a chiral molecule. And if you put in the left-hand form, maybe I said left, so let's say the light ray will actually rotate to the left, or you put in the other enantiomer, the light ray will rotate to the right. So now we have a way of figuring out which molecule is which. If you have a pair of enantiomers, put in one enantiomer, maybe the light rotates to the left, put in the other enantiomer, now the light rotates to the right. And now on your bottle, you can actually put a label, hey, this is a pair of enantiomers, but one form rotates light clockwise, that's the positive form. Another one rotates it counterclockwise, that's called the negative form. Chemists love putting names on every new thing, so the form that rotates to the right is called dextrorotatory, and the left one's levorotatory. And that's where we actually can get the D's and L's that you might see in biology. Biological molecules. All right, did I overwhelm you with too much information? Okay, what's the take-home message? Some molecules interact with light and rotate it left to right. Other molecules are not chiral and they don't rotate the light at all. That's all we need to know right now. Being a little bit more scientific though, you can actually measure this angle of rotation and report that as a value. That's one way to characterize molecules, to analyze molecules. And if you want to stop the video, you can read through this. It gives you some extra information about the experiment involving the polarimeter. But what I need you to know is that the data that you obtain will be an angle of rotation. So here turns out blood sugar is a chiral molecule. Glucose is chiral. The natural form is the D form with a positive rotation. That's the plus sign here. Plus sign here. So you can get we'll call it the right-hand form because this is dextrorotatory. The right-hand form, the natural form of glucose, pull in polarimeter, and hey, it rotated the light in a positive sense by 52.7 degrees, as long as you have everything else fixed. I don't want to get too deep in this, but I do need to tell you a couple things. If the chamber for the polarimeter is really, really long, the light goes through it for a longer time and gets rotated more. So the length of the tube will affect how much the angle is rotating. The density or the concentration will affect it, right? If you dilute it way, way down, then there's not that many chiral molecules for the light to interact with. If you use a pure compound, then it's going to be more concentrated and the light will rotate more, right? And also, it depends on the wavelength of light. If you change to a different color, the angle will change. So when you're doing this experiment, typically you'll use a sodium lamp and you use a filter so you only get the D line of sodium. So that's what this big capital D stands for, a specific wavelength of light. It's around 500 something, 527 nanometers maybe. I don't know, I'd have to look it up. And temperature affects it. So if they heat up the solution and cool it down, the angle will change. Okay, a lot of different variables to control. What I need you to know is if you ever see something that's similar to this, sometimes a D is missing, there'll be another number, or this might say 20, but you will see brackets with the alpha symbol inside with some other superscripts and subscripts. You need to recognize that as a measurement from the polarimeter, and we're talking about chiral molecules. And then the number that you get, the data, just look at the plus or minus sign. And then now you know if you have the right-hand form, which we have here, it's a positive form. So you can throw the plus sign in front of the name to identify it as that specific enantiomer. And then the value, it's kind of interesting. If it's a big number, it means, ooh, it's very optically active. If it's a small number, it's weakly optically active. And, you know, as long as there's some value, you know it's a chiral molecule. Cool. A little break there. Hey, let's look a little bit further, and maybe this is a test question you might see on your next exam. Explain why 2-methylpropane has this measurement. Okay, tough question because it's asking for you to do a lot of things. First of all, it's asking you to understand this, the IUPAC name. So propane is 3 carbons. Molly, it's about. PMET is 3, propane is 3, and then we number it. Remember, when you're drawing it, you decide how you want to draw it, how you want to number it. But on carbon 2, there's a methyl group. We'll draw it like that. And it says, hey, the measurement is this alpha with a bracket, 25D is a 0 value. So what does that mean? Well, this talks about optical activity. We put this molecule in the polarimeter, and the angle didn't rotate. That means it's not chiral. And the technical term for that is achiral, right? Scientists love a word for every new idea. So you have molecules that possess handedness, chiral. Everybody else is going to be called achiral or not chiral. Cool. That's an incomplete answer. You could say on the exam, hey, this molecule is not optically active. It's not chiral. And then I would follow up by asking, well, how do you know? Explain why it's not chiral. Okay, to do that, we have to learn how to predict chiral molecules. Let's go up here. Oh, you know what? I forgot something. Darn it. You know what I didn't do? I got this cool website. I found this YouTube link about polarizing filters. I'm sorry, I want to show you that real quick. Let's do that. So this rotating the lens here, blocking the light. Let me just show you that real quick. Because it's cool. It's a nice little break. I just want to make sure I am sharing the right screen. Yes. Let's listen to this guy explain polarizing filters for photography. So that's cool. So it turns out, you know, there's a whole bunch of light rays coming out of the sky, and the polarizing filter will absorb all the light rays except for the ones that are oscillating in one plane. I like this one the best. I'm not a very good fisherman, and I still haven't done it, but I hear that you can buy polarized sunglasses and it helps you see into the water. And you can see where the fish are. That's kind of cool. But here in this part of the video where he's rotating the lens, literally that's what you do with the polarizer. You just rotate it until light comes out, and how much you're rotating it, you measure that angle. That gives you your measurement. Cool. Alrighty, so come back to that test question. How do we explain, or how do we predict that 2-methylpropane is not chiral, it's achiral? And if you know it's achiral, then you can predict what the value will be. It has to be 0. Can't rotate plane polarized light. Must be chiral in order to do that. Okay, turns out there's 2 ways of doing it. I need you to know both ways. One way is going to be more popular and more useful, but it doesn't work all the time. So you need both methods. So first method, the less common way, is to see if you can find an internal plane of symmetry, which means can you cut the molecule exactly into 2 pieces that are symmetrical, that are the same. So let's go over here. You can grab a Erlenmeyer flask and cut it exactly in half. And yeah, the side that's towards us and the side that's away are exactly the same. But if you try and look down the, split a hand in half, well, one side has a thumb, the other side doesn't. And there's no way to kind of cut a hand in half to have 2 equal symmetrical parts. Okay, so that's a great test. Erlenmeyer flasks are achiral objects. A hand is a chiral object. And if you can find a plane of symmetry, you can rule out whether it's chiral or not. Now with the molecule, it takes a little bit more work. It still is a good test. We got propanoic acid here. You got the condensed formula here. If we expand it a little bit, that's CO2H. We're gonna have to get used to that. That's the abbreviation for a carboxylic acid. Now you have to see if there's a way to cut this in half. And so I'm thinking if we cut down the carbon-carbon chain, that's pretty symmetrical, but it looks like the top half has a double bond O and the bottom half doesn't. So you have to think 3-dimensionally. And right here, this is a C, and this one is the O of the carbon-carbon double bond, and it's up and down. And if you cut down that C double bond O group, and here's the O and here's an H, you can cut the carboxylic acid into 2 equal pieces. And then the CH2 group is right here, being cut in half by this internal symmetry plane. And this is clever. We have the methyl group at the end. And you need to spin the methyl group so that one of the hydrogens gets split in half, and then one hydrogen will be on one side, the other hydrogen will be on the other. And then, so yeah, we just found an internal symmetry plane. Here's another way to draw it and kind of see it. But just have to remember that, yeah, if you line up the groups, the atoms within the carboxylic acid, you can cut it in half. And so this molecule is symmetrical. There is a symmetry plane. Lactic acid, however, we saw earlier, that is a chiral molecule. And so if you line up the carboxylic acid group, you can cut it in half. This methyl group, we can cut it in half. But in lactic acid, there's an alkyl group. And in this alignment, in this shape, the alkyl group is going to only show up on the right side, not the left. And if you try and push this over and try and cut it with the, as you cut the methyl and cut the carboxylic acid, if you try and cut down the alkyl group, try and get two halves of the alkyl group, this hydrogen ends up on one side or the other. It can't be cut at the same time. It's impossible to cut the molecule into two equal parts. It is not symmetrical. We would say it's asymmetric, and it is chiral. Okay, just say it's chiral, and no internal plane of symmetry. That's a good test. On the other hand, a lot of students can't do this. You don't get a model kit on the exam, right? So this may or may not be the best method. A better method is this one. This is the more popular one, but again, doesn't work every time. So the method is, hey, chiral molecules usually have an atom attached to 4 different groups. Okay, so if you have your molecule, draw out all the bonds and see if you can find at least one atom with 4 different groups. Okay, be pretty loose with your definition of a group. It could be 4 different atoms, but it doesn't have to be. It could be 4 different functional groups. It could be 4 different types of branches, 4 different things. Okay, we'll do some practice with that in a second. Got a new idea. Hey, within a chiral molecule, there is this atom with 4 different groups. You need a name for that atom. Well, you can call it the chirality atom, or the chirality center, the stereo center, the stereogenic center, or the stereogenic atom. We couldn't, if it's chiral, we can't find a plane of symmetry. It's not symmetrical, so it's called the asymmetric center. I know, that's the one that's the most awkward for me, but if there's a homework problem that says, hey, identify the asymmetric center, I want you to be able to do that problem. The asymmetric atom, asymmetric center, is the atom with 4 different groups. I'll also just tell you, at this level of organic chemistry, I'm going to restrict the chirality center to a carbon. Right? Carbon likes to bond 4 times. It's ideal for becoming the chirality center. As long as those 4 bonds are attached to 4 different things, that makes it a chirality center, and that's going to help make it a chiral molecule. In the real world, though, other elements can be chirality centers. There's this cool little trick here we'll explore in a minute, that if you have more than one chirality center, you can actually predict how many different isomers, stereoisomers, you can have. For n being the number of chirality centers, use that as an exponent of 2. So 2 to the n power will predict the maximum, not necessarily the exact number of stereoisomers, but that's kind of useful. 2 to the n number of chirality centers help you predict the maximum number of isomers, stereoisomers there. Okay, let's do 2 things. First, let's get some practice finding chirality centers. And that will help us decide if the molecule is chiral. So, starting at the top here, is this a chiral molecule? Maybe. Try and find a plane of symmetry if you want to go back and do that other test. There's no way to cut this in half so that it's exactly symmetrical. Right? If I cut it this way, horizontally, the F and the chlorine are different. So it's already failing the internal mirror plane. It's probably chiral. We can use a second test, though. Are there 4 different groups on an atom? Well, the halides only bond 1 time, so don't check those atoms. Check the carbon here. So carbon, where are your 4 bonds? There's a bromine, fluorine, a chlorine. That's 3 bonds. Oh, this is a skeletal drawing. So there's the unwritten hydrogen. 1, 2, 3, 4. Everybody's different from the other. Yes, I'm going to circle that. Here's my chirality center. And ooh, if you're showing your work on the exam, don't circle these. I should have put squares around them or something. Sorry. Be a little careful on the exam. Okay, here's my chirality center. Maybe we should put an arrow. How about that? So that would be fine to do on the exam. Be very clear in your answer. Yikes. Next one, moving on. Any chirality centers here? Well, I kind of see the letter X here. I need an atom with 4 bonds. And there's an atom with 4 bonds, kind of like an X. So that visually is a way to find chirality centers. But now you have to check. Is this carbon chiral? Does it have 4 different groups? Well, there's an iodine and a chlorine. They're different from each other. This is a carbon. That's a carbon. Doesn't look too different. Not atoms, though. Doesn't say 4 different atoms. The definition is 4 different groups. So at the end of this line is an I. At the end of this line, there's a Cl. What's at the end of this line? This thing right here. What's at the end of this line? An ethyl group. 4 different groups. This is a yes. That is a chirality center. It's got an iodide of chlorine, a 2-carbon group of the bromine, and a 2-carbon group, ethyl. All 4 are different from each other. Yay, there's the chirality center. Am I done with this molecule? No, this is a letter Y over here. So I tell my students, look for X's and Y's. Well, that kind of looks like an upside down Y, but sort of a Y. Check this one here. What do we got? Well, going up this bond is bromine. Maybe we should change colors. Okay, so we're going to check and see if this is also a chirality center. Well, it's got a bromine on this bond, and this bond is a methyl. What's on this bond? The rest of the molecule. That's the group attached to this chirality center. I already know, huh? There's also the unwritten hydrogen. And I check Br, CH3, H, crazy group. Yeah, those are 4 different things. Circle this one, maybe put an arrow next to that. There are 2 chirality centers in this molecule. I should have checked this one though. This has 2 groups on it, but there's 2 identical hydrogens also. So this is not chiral. What about this methyl group over here? Is this a chirality center here? No, there's 3 identical hydrogens. That is not a chirality center. So in your skeletal drawings, look for these little intersections that look like a Y or intersections that look like an X. Good place to check. Cool. Here's another molecule. Are there any chirality centers? What about this carbon right here that's double bonded to oxygen? Well, 2 ways of saying no. This bond connects to O and this bond connects to the same O. Okay, it doesn't have 4 different groups. You could also say this carbon connects to an O, a C, and more, and this one connects to a C and more, and where's my 3rd group? There is no 3rd, oh, sorry, 4th group. There is no 4th group. That's not a chirality center. The carbon connected double bond O. How about this one over here? Is this a chirality center? Nope. This carbon has 2 identical H's. So there's this one, and this one, and this one. This looks like a letter Y. Ooh, that's what I should have looked for. This intersection looks like a letter Y. So let's check this one. Let me change colors. So maybe I can clean up the screen real quick. That does look better. Okay. Let's check this one, the little Y intersection. We have a methyl group. Going up this bond, there's a double bonded O and all of this. Sorry. That just says something. Remind me I'm going long. Rings are a little different with chirality centers, but just start the ring going this way. You see there's double bond O, and then on this bond, I immediately don't find a double bond O. This side of the molecule is different from this side. Mentally, you can kind of break this bond here and say, okay, I got 2 carbons with a double bond O. I have 2 carbons with not a double bond O. They're different from each other. And methyl is different from those 2 things. Wait, that's only 3 groups. Oh yeah, this is a skeletal drawing, so there's also the unwritten hydrogen, which is different from the other 3. And yay, that's my chirally center. Lastly, is this molecule chiral? Is there a chirality center? Looking for X's and Y's, and the only one that might be chiral is this one. Everybody else, all the other carbons, have at least 2. Some of them have 3 hydrogens. So these other carbons of the chain cannot be chiral because they have 2 identical groups, 2 H's, or 3 identical hydrogens. This one, though, has a methyl, has an ethyl, has a propyl, and has a butyl group. Those are different. This is a chirality center. This molecule is chiral. If I ask you to draw the 2 structures, the 2 enantiomers, the 2 stereoisomers, all that good stuff, you are now forced to draw dash and wedge bonds. This one drawing has 2 isomers in it, 2 enantiomers. So you would have to draw, let's see, I got the propyl, then the chirality center, and then I have the butyl group over here. How come that looks different? It just is. I got a high ethyl group up here. Maybe I'll make that on a wedge bond. And the dash bond will be to my methyl. And if you just leave a dash bond dangling or a wedge bond dangling, the end of the line means carbon. And I want to draw it pretty much the same way, but now make the dash bond go up to ethyl and the wedge go down to methyl. And then now I have the 2 enantiomers. Cool. A couple more ideas before I end this video. One, let's explore this predicting power of how many stereoisomers are there and why do we have to qualify it by the word maximum? Here's a good example. Draw all stereoisomers of 1,2-dichlorocyclopropane. Okay, to break this problem down, I would first just draw a simple skeletal drawing. I got the cyclopropane part. Next, I need to put on dichloro. Oh yeah, that's 2 chlorines, di, that means 2, and put them on carbons 1 and 2. Now when you're drawing, you decide where carbons 1 and 2 are. I'm picking the bottom. So there's a chlorine, pure skeletal drawing. I got 1 drawing, but it wants me to find all of them, all stereoisomers. So what I want to do next is find your chirality, find the chirality centers, and use that as an exponent of n. And that's going to give me the maximum number of stereoisomers. So, are there any chirality centers? Well, look for Y's. Right here, that's kind of a letter Y, kind of. But anyway, it's an intersection of 3 lines. So let's check this one. Got a chlorine. I go up here, I got a CH2 group. I go around here, I have a CHCl group. That's, these 2 pieces are different. And then there's also the unwritten hydrogen. So yep, that's a chirality center, I'll circle it. If you check this one, exact same pattern. Chlorine, carbon with no chlorine, carbon with a chlorine. And this one also has the unwritten hydrogen. There's 2 chirality centers. What happened to my letter S? Okay, found 2 chirality centers, so 2 to the 2nd power equals the max of 4 stereoisomers. So let's draw those 4. To draw the enantiomers, we need to use dash and wedge bonds. And use all combinations. So as I connect 2 chlorines to cyclopropane, let's use all the combinations of dash and wedge bonds. Okay, so I'm going to just be systematic, kind of follow a mechanical way of thinking. Let's start with 2 wedges and 2 dashes. Let's do wedge first, then dash. And let's do dash first, then wedge. Cool. These 2 and these 2 are different from the other pair, right? In the first 2 drawings, the chlorines are above the ring or they're below. Those are the cis isomers. Here, 1 chlorine on one side, chlorine on the other side. Those are trans isomers. I got my 4 isomers. Yay, I can walk away hoping for full credit. And oops, on the exam, I lose a few points. What? I did draw all the isomers. Okay, so we need to qualify this. I might have to ask, how many actual isomers are there? Try the symmetry plane test. If you cut this right here and this one right here, they're exactly the same. The 2 pieces are the same. This is an achiral molecule. So is this one, achiral. In fact, these are the same molecule drawn twice. And I should have built my model ahead of time. Let's see. So, making a lot of noise. Let's stop sharing. Got cyclopropane here. There's its flat. Let's put 2 green. Green will be chlorine. Going towards or up. There's my other green one. There it is. Cool. 2 chlorines pointing up. That's cis. 2 chlorines pointing down. That's cis. This is the same molecule. So if I hold it like this, the chlorines are coming towards you. Rotate this way, the chlorines are going away. That's the same molecule drawn twice. Towards us, away. Okay, so I drew the same answer twice over here on the left. There's only 1 cis isomer, and you can draw with both chlorines towards us or both chlorines away. What about the trans? Isn't there a symmetry plane right down the middle too? Nope, wedge is different from dash. These are in fact a pair of enantiomers. Enantiomers. I know I'm late. Here's the green. Okay. I'm gonna take my cis isomer and make it trans. Grab this one, put it down here. I should put in the hydrogens, but I didn't make it ahead of time, so I'm not going to. I can't twist this to try. I mean, I guess I could, but in real life, if you twisted the molecule this far to get the chlorine on the same side, you'd break the ring. You can't twist it so that the chlorines are on the opposite side, or on the same side if you start through a rotation. Okay. I'll make the trans one. The other isomer. Yep, there we go. Okay, so there we go. Hold them up like that. Oh, I got grabbed the wrong color. Did I tell you I'm partially colorblind? But I can see that it's different. So pretend they're all green. Yikes. Okay, if I rotate this way, things are not lining up. Everything's in the way here. So it'd probably be better for you to get your gumdrops and toothpicks, make your own models to convince yourself that there's no way to rotate this so that the chlorines are oriented the same way. No, it's just not working. These are not superimposing, and yet they're mirror images of each other. Other than the miscolor, they are a pair of enantiomers. Okay, so the total number of stereoisomers for 1,2-dichloropropane is 3. So if I want to circle them, here's one stereoisomer, here's a second stereoisomer, and then you pick one of these. I'll pick the first one. Actually, 3 stereoisomers. We predicted a maximum of 4, turned out stereoisomers. Turns out there's only 3. Hey, let's end the video, because I've gone way over. But this last idea, why is this relevant? Why do we have to do this? Well, it shows up in biology, biochemistry. So one idea, one application is in enzyme chemistry. Enzymes are nature's catalysts, and they turn out to be really big proteins that are wrapped up into a 3-dimensional shape. And then they grab onto molecules and react with them, cause a reaction. They speed up a reaction. They're catalysts. Nature's catalysts, I think of as enzymes. And they're very specific. They don't react with every molecule. They only react usually with one molecule found in the body. And it turns out they kind of act like a lot. In the enzyme, there'll be a little pocket called an active site or binding site. And the molecule that the enzyme is targeting fits snugly in there. This is actually an oversimplification. You have to take some biochemistry to get a better explanation, but this is the basic idea. If a molecule doesn't fit, it doesn't react. So over here on the right, we got the same situation. This blob with a letter L carved into it, this represents the enzyme, the protein. And then here, this L, maybe think of it's made of metal and it's got a handle on it. This is the normal molecule. And then here's the mirror image. The L is backwards. And if you hold up a mirror, one's a reflection of the other. And then if you grab the handle here and stick it into the binding site, it fits, but not the mirror image of it. The one that's nearly identical. It's got the same, it's got both of them have the letter L's, both of them have handles, just like molecules can have a left hand and a right hand form. But there's no way to get this molecule to fit into this binding site. If you flip it around so that this looks like a letter L, the handle gets in the way. So it turns out only one enantiomer can bind with an enzyme. So there are some, and way back in the day, and maybe even today, we gotta be a little careful as people, pharmaceutical companies create new drugs. It's very easy to make chiral molecules, and chiral molecules are very similar to each other. It's very difficult to separate. So in some cases, they actually sell the mixture of the 2 enantiomers. One enantiomer binds to the natural enzyme or binding site or receptor in our bodies, and the other one won't. What does that one do? It goes and binds somewhere else and causes a side reaction or a side effect. So if some medications make you feel funny, you break out in hives, one mechanism, not the only mechanism, is that maybe it's a mixture of compounds. A racemic mixture is the term for that. And the enantiomer that is not binding, not doing the bioactive role that you're binding the drug for, maybe it's interacting somewhere else. Nasal receptors, the sense of smell, are also proteins. And so here's a pair of enantiomers. It's called carvone, and the difference is right here. Here's our chirality center. So on this wedge bond, there's this group, this half of the molecule, and this half of the molecule, and the unwritten hydrogen. It's got 4 different groups. That makes this a chiral center. And if this double bond alkene is on a wedge bond, that's one form, we can switch it to a wedge and get the other enantiomer, the other mirror image. And they're different. Put this one into a polarimeter and it rotates it counterclockwise. Ooh, here's a notation for optical rotation. Yeah, and that's not 0. This is a chiral molecule. But we already predicted that, right? We already found the chiral center. Notice the boiling points are exactly the same because they're really, really similar. On the other hand, you can tell them apart because your nasal receptors contain proteins, and proteins are chiral. It's like shaking hands. This chiral molecule, well, it's an odor found in spearmint plants. You harvest the spearmint plant, get this molecule, put it in a chewing gum, say, oh, this is minty fresh. And this molecule is coming out of the chewing gum, going into your nose, and binding certain molecules. Like we saw up above, only certain receptors can bind certain molecules. And I think the sense of smell works where you have this molecule binding several receptors, and the pattern of receptors that get bound to sends a signal to the brain, says, spearmint. You take the enantiomer, the mirror image, that actually comes from caraway seeds. So here on this, I think it's a Reuben sandwich made with rye bread. You can see little seeds. Those are caraway seeds. And it has a distinct flavor. So if you bite into just the bread here, you'll say, that's rye bread, not white bread or wheat. It has this kind of a cool fragrance, cool taste. I would not say it's minty though. It turns out that this molecule is a mirror image of that one. So when it goes into our nose, it binds to different nasal receptors and sends a different signal to the brain. It says, not minty fresh, you're having this type of sandwich with rye bread. And the only difference is the orientation, 3-dimensional orientation of this group. Isn't that cool? All right, that's enough for now. Thanks for watching.